But yeah, okay. So yeah, I'm just gonna take a back seat. You guys can discuss. The first problem is just sketching out the architecture. This should be really easy. This should be the easiest problem. My mom got me some chili mango, dried chili mango in the store. So that's what I'm enjoying today.
They're spicy.
It's like, I guess I have a decent spice tolerance because there's a lot of spice in Indian food. But if I'm being, it's not super spicy, right? But if I'm being honest, I kind of enjoy like the sweet. I just like regular dried mangoes. It's just nicer, I think. This is cool too, though.
So like the input layer would be just x1, x2, and then yeah, and then the hidden layer and then the output layer, right?
Sure, I guess. Yeah, that was like super vague. You're right about the
Yeah, it
input
wasn't
layer,
my best description.
You're spot on with the input layer, yeah.
So I know like this problem gives you the like number of nodes in the hidden layers, but I think we went over this a little bit last time, but how do you decide what the best number is for how many like neurons you want in your hidden layers? I know like as you propagate outward, we said like normally you would just divide by like 2, but how do you decide that like initial one?
The initial one, like the hidden layer, initial hidden layer,
Yeah,
right after
the first hidden layer, yeah.
I don't have an answer for you, unfortunately. And actually no one does. There's just no answer. There's just rules of thumb and there's just like intuition. And these are just kind of things that you learn from just trying a bunch of random network architectures and kind of thinking about, like, remember last time? So last time we were doing image stuff, and it Pilar, you were the one who started from input size and then just divided by 2 every time. That was you, right? I believe, or was that Lauren? No, that was Lauren.
I think that was me.
That was Lauren, and then Philip, you did like 128 to 64.
Mm-hmm.
Yeah. So, like, I would have nothing wrong to say to either of those. They're fine. It just so happened that Lauren's design of starting from the input size and dividing by 2 just did a little bit better, and it was like, I don't even know if it was like 1% or like a fraction of a percent better. Yeah, something like a fraction of a percent better. But usually that's just how I think. Like, how I think about it is like, okay, what is the size of the input layer? What is the size of the output layer? If it's, so in the case of image classification, it's obviously this huge reduction, right? You have like this 28 by 28 size image, so that's like 784 or something pixels, and you want to go all the way down to 10. So in my mind, I think, okay, yeah, I want the hidden layers to slowly or quickly, I guess, get there. But like in this case, so we're going from 2 to 1, right? But obviously, like if we had like a hidden layer, if we just went from 2 to 1 to 1, like actually, I don't know how it might do okay. But just thinking about, like, you just kind of think about like, how complex is this problem? Like, how many factors do I think really play into this? And at this point, everything that comes out of my mouth, I'm just kind of making it up. But like, you just kind of think about the complexity and say, like maybe 3. Let's try 3. And you just try it. You just try it. See what happens. But yeah, in this case, we're given then it's 3. So you guys, do you guys have a final network architecture? Like the circles? Okay, so yeah, 2 for the input layer, 3 for the hidden layer, and how many for the output layer? Yep, just 1. Just that final prediction. So yeah, that was the easiest one. And then we have, what is this? We have a predicted probability versus binary cross entropy. This is showing the same thing I had in that slide, where if the actual, when you see that loss LY1, that's just saying the loss of the predicted Y hat means the guessed Y. And then the second number 1, that's like the actual Y. So in this case, it's a 1. So yeah, this is just showing that if the predicted probability of being a 1 is super close to 0. The closer it is to 0, it exponentially shoots up the cost. Because that's like saying like the network's super confident that it's a 0, which should be penalized more than if it was like 0.6 or whatever. The figure on the right, weight value versus sigmoid activation. Yeah, this is just a graph of the sigmoid. You guys have seen that before. So yeah, it's saying binary cross entropy for the loss, sigmoid for our activation function. If you guys have a calculator, that'd be helpful, but you can always just type stuff in Google. But we will be doing like, yeah, some actual number crunching. So this part where it's talking about like the reciprocal rule and stuff, you don't have to worry about it too much, but it's basically just talking about the derivative of the sigmoid function and how to derive it. This is more calc stuff. So maybe surely this will be a good exercise for you to look over like, what is the derivative of sigmoid? Why, how do you end up at that? But it's kind of neat. It's just like sigmoid happens to be one of those functions where its derivative can be described in terms of itself. So the derivative of the sigmoid function is itself times 1 minus itself. And that's just all that it's showing in this section.
So I thought you apply the activation like sigmoid function to like the z value after you've calculated all the weights with the bias value, right?
Yep. Yeah, so if you see W and you're confused because you think like, oh, does W mean weight? Maybe that should be more clear. W does not mean weight there. It's just some variable. In this case, it would be Z. Yeah. Maybe it'd be more clear to put Z there. Yeah, it kind of changes from like Z, from W to X. It's like all over the place, but yeah.
So figure 2 is like mapping the weight value to like a sigmoid activation function. So is the weight value here talking about like the Z value kind of, or?
Yeah. Like just think of like, yeah, just W should be Z. W should be Z, and then the activation would be F of Z. And that's what you saw in the video written as A for activation. Yeah.
For problem 2, do you just like plug in the numbers? I'm kind of confused how you're supposed to show that like x1 equals -1 and whatnot.
Sure. So first of all, what is x1 without the bar? This is given to you.
It's a value. Oh,
yeah, and it's given to you.
The sleep, right?
Yeah. I'm asking
Okay.
for like the literal example, like what's the number that was given to you? It's in the problem statement. It's all the way at the top.
Right. It's the x1 squiggle n. Is that not what you're saying?
No, I'm saying so what we're doing in this worksheet is basically we're running one example, one student, and their amount of sleep and all that stuff through the network once, and then we're backpropagating it. So I'm asking this specific student, what is their x1 and x2? And
-1.
Oh no, not the bar. Like
not the bar?
Yeah, it's at the top. It's at the very top of the worksheet.
It's in like problem 1.
Oh, it's all up there. Oh, okay. I was like, how do you get these numbers? Okay, thank you.
Yeah, exactly. So yeah, the amount of the number of hours that this student slept before the exam was 6.
Right.
And then yeah, how much did they study before the exam?
5 hours.
Yes. Making sure you're on the same page. Okay. Yeah. And y equals 1, representing that the student did indeed pass the exam. So that's what we're using. And do you understand how to standardize it given the normal distribution?
I think so. You just plug it in that equation.
Yeah.
Okay, cool. Thank you.
But I mean, I guess I should have rephrased that question. Like, does the normal distribution notation make sense to you? Like squiggly and mu equals 8, sigma squared equals 4. Like, does this, how about this? Like, could you tell me in words, like how would you read that out? Like the squiggly and all. You obviously wouldn't say squiggly, but does anyone know how you would say that in words? Like the x1, how about that? Like,
Isn't this like normal distribution with like the middle, the mean at 8, and then the standard deviation would be 2? Because the variant, it's basically like, it's approximately normal distribution with a mean of mu and a variance of sigma squared.
Exactly. And I like that you said standard deviation of 2, because the standard deviation is a square root of the variance. And we always write the normal distribution with mu and then the variance, which is sigma squared. But yeah, the variance is 4, but then the standard deviation, which is sometimes more useful because it's in the same units as the actual thing, is 2. Yeah. So how I would read this out is x1, tilde means is distributed as, n means normally, and then mu means average, sigma squared means variance. So in English, this would be x1 is distributed normally with a mean of 8 and a variance of 4. That's basically the math to English translation of that. So how's the progress on problem 2? Did you guys all verify that? Did it make sense and you got the same number? Same nods? Okay, cool. So you guys are on problem 3 now.
Can you explain the weight matrix? I'm a little confused by that.
Sure.
Sure. Like at the bottom of page 2.
Yeah. So the weight matrix is, well, how would you read out the dimensions of W1? It is a n by m matrix. How would you read that out? It is a what by what? A 2 by 3. Yeah, we always go, yes, exactly. We always go in the shape of an L, down first, then to the right. So it's a 2 by 1 matrix, and that obviously corresponds to 2 neurons in the input layer. Sorry, did I say 2 by 1? I meant 2 by 3. 2 in the input layer, 3 in the hidden layer. So then, so each value is going to be one of those connections, because there's 6 of them, obviously, between the 2 and the 3, since it's a fully connected layer. So just take a guess, like what would the very first element be? Like, what do you think it would be?
Is it, so it would be the weight of the connection between the first input and the first, like the top neuron in the hidden layer, right?
Yeah, exactly.
Oh, and then you just work through. Okay, I see.
Yep. And then that's the easy one, right? Because it's obviously the first one, but the less easy one, or like this is the one that really concretes, like, what is the direction? What would the second, or actually, which one should I ask? What is the one below it? The number below the very first entry, not to the right, but below.
I'm assuming it's the connection from the second input to the very top neuron in the hidden layer.
Yes, correct. Yep.
Oh, I see. Okay.
So now you know, and now given that, you can figure out like what the rest of the numbers mean.
What is weight 2 again? So
So what is the shape of weight 2?
It's a 3 by 1.
Yeah, and what does that correspond to? Why is it 3 by 1?
Is that just the weights at the hidden layer?
Well, why is it 3 and why is it 1? Why is it not any other number? Look back at your neural architecture.
Well, the second weight. Oh, it's the connection from, oh yeah, that was dumb. It's the connection from the hidden layer to the output layer.
Yeah, exactly.
Okay, yeah.
No, it's not dumb. This is really, really important to make sure that you understand, like, why do we represent it as a matrix? because it's just the most straightforward way of just shoving a bunch of numbers in like some sort of table to represent. And yeah, the indexes matter. It's obviously very, very important to understand. But yeah, that's why it's 3 to 1.
Got it. That makes sense. Thank you.
So what's the input column vector x? What vector are we passing? And the column vector should be standardized. Are you guys still working on that? It's fine. I'll give you more time. So how about this? What should the shape of the input vector be?
2 by 1?
Yes. Yes. 2 by 1. And the first element should be what?
Negative
in terms
1.
Of,
or
yeah.
Or
yeah.
Okay. X1.
Yeah, correct. X1 standardized.
Yeah.
We say X1 bar.
Bar?
Bar. Yeah, because
Okay.
there's like that little bar over it.
Yeah.
You see?
Yeah.
Yeah, so bar just means standardized.
All right.
So yeah, -1, which means obviously that the bottom number is 1. So that's our input vector. Okay, forward pass. So at the hidden layer, we multiply the transpose of the first weights matrix with the input vector. Okay, someone remind me what the transpose is. What is the transpose of a matrix? Not Philip.
You flip the column and row.
Yeah, you flip you can just think of like taking the matrix and just rotating it, doing a reflection over the diagonal. Yeah, not rotating, that's wrong. But reflection. The ith row becomes the ith column and vice versa. Why do we transpose it though? This one's a little bit harder. You can attack this 2 ways. The easiest way would be talking about dimensions. What is the dimension of W and what is the dimensions of X? Well, we said the dimensions of X. X is 2 by 1. Lauren said that. What is the dimension of W1 again? You can like look
2
at
by
the
3
worksheet. 2 by 3. Yeah. But remember, when you're multiplying 2 matrices, what condition must hold regarding the dimensions? This is really important. If I want to multiply 2 matrices, the order matters, right? So what dimensions must they share in common?
The number of columns in the first one has to be the same as the number of rows in the second one.
Exactly. The number of columns in the first or the left matrix has to be the same as the number of rows in the second or the right. And so order does matter. AB does not equal BA. So that being said, W1 is a 2 by 3 matrix. X is a 2 by 1. We cannot do matrix multiplication that way. So we transpose W, and then what does its dimension become? Its dimensions turn into what?
3 by 2.
Yeah, and so if you multiply a 3 by 2 matrix by a 2 by 1 matrix, what is the final result? What are the dimensions of the final result?
A 3 by 1?
Yes. Yeah, it's a 3 by 1. It's a 3 by 1. That's why they have to share that middle dimension. Because that middle dimension is going to get canceled out. It has to be the same. So, and I'm sorry for sounding like a broken record. I truly am. But like it's just going to help you so much. Like this was the most important lesson. Really, this was just the most important lesson for you guys to have been comfortable with lesson 0. I don't know, like, you know, how much time you spend with it, but for real though, like if you guys are and like also, I mean, going into later classes, you guys are probably going to take linear algebra, probably are going to, if you guys are, yeah, I mean, most of you guys are doing CS in one form or the other, you're probably going to take some sort of machine learning class, or I mean, Shirley's literally a freshman first semester. She's doing gradient descent. Like, I promise you, like if you make flashcards out of lesson 0 or just like study it really well, I promise you, you will just be so much better off. Like, just trust me on this one. It's like, I'm really not even just saying this because I wrote it. Like, it's this stuff. Like, if you knew it, then you would just know right off the bat. Okay, yeah, I mean, the middle, you know, the whole columns and the row things that Lauren that you said, like that should be like you should have that. You should have that off top, and you'll just be so much better for it. So yeah, so it makes sense why we transpose it now. And applying
I have a quick question on that.
Yeah, for sure.
So I know in linear algebra it's not like you can't just flip the terms. Like you can't, like WT times the transpose of W times X isn't equal to X times the W of transpose. Why do they multiply the W of transpose first? Because if you did like X times W of transpose, then like wouldn't the multiplication work? So like it would be easier, but I guess there's a reason that the weights are multiplied first.
Would X times W transpose work? What is, okay, dimensions of X 2×1. What are the dimensions of W transpose?
Oh yeah, you're right.
Yeah.
Never mind.
But you might say X times W works. Why not X times W? X is 2×1. W. Oh wait, W is no, never mind. That also doesn't work.
Yeah, so, yeah, that's actually what I meant. Instead of, but like, yeah, I guess it doesn't work out anyway.
Yeah.
So, whatever.
So just as a quick check, so what are the dimensions of Z1 again?
3×1?
Yeah, correct. But F is a sigmoid function, right? So what does it mean to apply sigmoid to a vector? Because usually we really just think of as plugging in one number, right? So what would it mean to do sigmoid to a vector?
Doesn't it just affect every single value and put it between 0 and 1?
Yeah. No, it was an trick question. You basically just you apply sigmoid to each element. That's what we call like an element-wise function or whatever. But yeah, because like sometimes functions do depend on the dimensions, but in this case, and like a lot of the times, if you see like a scalar function being applied to a vector or a matrix, the most natural thing to assume is just, okay, just do that function to every single input. And yeah, that's what we're doing here. Okay, so we're on problem 4, and if you guys read everything in between, then does everything make sense? Any questions about everything before problem 4? And if not, then we can just work on that.
So the whole point of like biases at every single layer is kind of to account for like unknown like variables that could kind of impact the prediction, right? Or I think you're muted.
My bad. So think of it like I always try to just remember y equals mx plus b, right? Mm-hmm. So like let's say that you had some data points and you're trying to fit a y equals mx plus b to it, but then let me see if I can actually whip something up in Paint like really quickly, because if I can do this, it will help you. But basically, it's just like shifting the entire input, because maybe you have the right slope, but you just don't have the right y-intercept. Does that make sense though?
Right.
Okay, I whipped up Just gonna, I'll show off my paint skills a little bit. Okay, can you see this? Oh, wait, it's showing. All right, so this is like one mx plus b term, right? So let's say like these are the two data points that you're trying to fit it to. Like, as you can see, the slope is perfect. Like, it's the perfect slope, but then you just want to shift this whole thing up.
Right.
Yeah, or down. I hope my paint skills helped. But yeah. Are you guys on problem 4 or problem 5? Just, you can like let me know. Raise your hand. What does that mean, Lauren? Is that sign language or something?
6.
6? Is that like
never seen
sign
that
language?
Are you serious? Wait.
What?
Does anyone know this
Is
is
that
6?
is that American sign
It's
language?
not
Or is
sign
that...
language.
No, I've definitely never seen
Yeah,
that.
nobody
Never.
knows what you're talking about. Nobody knows what you're
Wait,
talking
Shirley. What number is this? Are
about.
you?
She has no. This
Let's
means
hang
radical.
loose.
This
Yeah.
means hangs
this
loose.
is
I'm shocked.
Is that like a common thing?
Yeah. Wait. Like
You meet
No.
someone and they're like, "Yo, what's going on?" And you're like, 6? Like, what are you talking about 6? Like, what? They're like, "No, like hang loose."
I've never had this problem. Okay, wait.
Okay, what's 7? What's 7? So
It's just
okay,
like
so
1,
this
2,
is 2.
3, 4.
So this is like a 5. This is like a 5, and then it's
5.
like, oh wait, no, what?
6, 7, 8. Okay, I just looked it up. Apparently, it's a Chinese hand gesture. So,
There
I
you go.
guess we, as in Chinese people.
It is a smart gesture. Like, it's efficient if you know it, I guess.
Yeah, that's true. That's true. It's efficient.
I was just gonna ask, like, how do you round? You just like can round to the.
Oh, straight up, just
Okay.
yeah,
Sounds good.
yeah. I like how that answered your question. I was gonna explain, but yeah, I mean, straight up, yeah, straight up. Less than 0.50, more than 0.51.
I'm done with 8, so you can go ahead if you want.
Let's do it. Okay, part 4. Now this is the fun part, the actual backpropagation. So we made the wrong prediction. Hopefully you guys saw that. I mean, rounding down the 0.491 to 0, and we wanted 1. So this delta term, that's just what we use for error, and that's what is going to affect our. So like the delta from the last neuron is straight up just the difference between what was guessed, the probability of being 1, and 1, just 1 minus that. And then everything before that, it's the whole chain rule stuff. So 4.1, for the output layer, we apply the chain rule. Delta 2 is going to be the derivative of the loss with respect to the guess times the derivative of the guess with respect to the pre-activation. And let me know if you guys are confused about any of this intermediary stuff. I can definitely go over it if you want. But yeah, so like all he's showing is, you know, plugging in those values. The loss is the negative log probability, also called binary cross entropy, but negative log is more descriptive. And the guess is just the activation function put onto the pre-activation, aka z, so f of z. And this is what I was saying earlier about the derivative of the sigmoid function being itself times 1 minus itself. So that's why you see f of z2 times 1 minus f of z2. That's just the derivative. And quick calculus check. Where did the negative 1 over y come from? Where did that come from? Why is there a negative 1 over y? How did we get from derivative of negative log to negative 1 over y?
Just the derivative of natural log is 1 over y.
Yeah. Yep. Yeah, that's just a chain rule. You just multiply them together. And substituting for y, that's just showing that at the end, these are actual numbers we're dealing with. The guess was 0.491, that's y hat. And yeah, you just negative 1 over y times y cancels out, so negative 1. And then 1 minus y. So we did all that just to find out that it's literally just 1 minus the guess. But it's not as easy in the previous layers. So for the hidden layer error, this is where we actually get into more terms in the chain rule. So we have the same two terms from before. The derivative of the loss with respect to the guess times the derivative of the guess with respect to the pre-activation. That's just from last time. But this time, now we want to go further backwards, back propagating. We want to see, okay, well, times the derivative of the pre-activation with respect to the activation of the previous layer. And what is the derivative of the previous layer's activation with respect to its pre-activation? So that's all that stuff. So make sure you guys are careful here when you're number crunching, because that star means element-wise multiplication. We're not doing matrix multiplication. I guess that's somewhat obvious because we're not even dealing with matrices. Like A is obviously a scalar. It's like an activation. It's just a number, a scalar. It's not a matrix. But yeah, that's why it's element-wise.
So this is basically the like the numbers basically represent how much impact each like specific weight has on the prediction.
Yes. Yeah, it's the error, the sensitivity, same thing. So like how much of the loss is due to each neuron. Yeah.
Okay, so if so like for problem 9, like negative 0.0255 and 0.0431, that means that the second, like 0.0431 is having more of an impact on the loss function than like the other two, because the other two are negative, or is it?
It's the magnitude, so sign is not really. Sign just says which direction, but
which direction, right?
Okay. Oh, I see what you're saying. Yeah, like which direction. Yeah. I mean, you're right either way. Yes, you're right either way. Like, so just to confirm, the first element is saying like, if the weight from the first hidden layer node to the output layer was positively increased a tiny bit, whatever that bit is, it would increase the overall loss, the overall error, by negative 0.02 times that bit. If that makes sense.
That makes sense, yeah.
Should I go over the intermediary thing, the number 5, the gradient descent? Did you guys already read that stuff? Yeah, okay. So now that we have the error terms, we will apply the gradient descent algorithm. So first, we calculate the gradients. And this is just the derivative with respect to loss. That's basically what we've been doing. But, okay, so first let's do it with respect to W2, which is the weights for hidden layer to the final output layer. And so to do so, we just multiply the input to the output layer with the error of the output layer node. This is just, the derivative of the loss function with respect to an entire matrix. And you might be thinking, like, what does it mean to take the derivative with respect to a matrix? But once again, it's just element-wise. You just take the derivative with respect to each element. So pretty much what you might have guessed. So similarly, we calculate the partial derivative of the loss with respect to W1. This represents the gradient of the loss surface at the point W1. So yeah, if you like think of the matrix as a point in space, then this is showing how much, which direction should you move from that point in space to increase the gradient the most. So that would be denoted the same way, dl over dw1. And it's x times the error of the first layer transpose. And that, once again, that's just to make the dimensions work, right? So yeah, show that derivative with respect to W1 is that matrix.
So what you're saying about like stochastic gradient descent, when the batches are, let's say there's like 1,000 different samples and the batches are 10, it'll just take like 10 random samples and then like smush them into, like take the averages of those and then just propagate it through so that you only have to do it like 100 times rather than 1,000, right?
Exactly. Yeah, you just pretty much explained it exactly. Yeah.
It's interesting.
Yeah, it saves a lot of computation. It's just kind of like, okay, I don't want to pass in each of these examples one by one and backpropagate and do all that stuff. So I'm just going to do a shortcut, average them all together, and you just keep doing that. How are you guys doing? Did you guys get problem 11? Yeah, cool, okay. Problem 12, is that what you guys are on now, or even done with that? Problem 12, okay. A couple of you guys are done, but sounds good. So yeah, I mean, this part is just straightforward. We're just doing what we did last time, but just this time we're checking, okay, did our, our improvements work? Spoiler alert, they do. They work. They work well.